In this video, we will introduce two LU factorization methods for solving systems of linear equations. The LU factorization methods rely on factoring the coefficient matrix A into a lower triangular matrix L and an upper triangular matrix U. The product of L and U is equal to A. When finding the elements of L and U for an n by n matrix A, we must find n unknowns. In the Doolittle method, the diagonal elements of the L matrix are all equal to 1. Both of the LU factorization methods introduced here are based on a similar algorithm. We first find the matrices L and U, and then we use forward substitution to find the elements of a vector y that solve the equation Ly equals b. Since the matrix L is lower triangular, this can be done using forward substitution, solving for one element of y at a time. We begin with the first row to solve for y1. Once we know y1, we can solve for y2, and once we know y2, we can solve for y3, etc. We use back substitution to find the elements of our unknown vector x by solving the equation u times x equals y. These substitution operations are straightforward, but it's the factorization into the lower diagonal and upper diagonal matrix that are the trick for the LU factorization methods. For a 3 by 3 coefficient matrix A, if we define A equal to the product of the matrices L and U, then we can write a system of 9 equations for the 9 unknowns. A11, A12, and A13 should be equal to U11, U12, and U13. In the second row, A21, A22, and A23 should be equal to these products or a product summed with an element of U. As the coefficient matrix A gets larger and the number of rows increases, these equations look more and more complicated, but they can actually be done quite quickly. A simple script for the Doolittle method of LU factorization is given in the methods text. This script works for any n by n coefficient matrix A and requires only 9 lines of code with 2 nested for loops. The LU factorization requires 1/3 n cubed operations for finding the elements of L and U, where n is the number of rows in the coefficient matrix or the number of unknowns in X. The substitution methods require approximately n squared operations as n gets large. Therefore, for large n, the total number of operations for the Doolittle method is 1/3 n cubed. Notice that this is about half of the number of operations required for Gauss elimination. Therefore, the Doolittle method can be done in half as much time as Gauss elimination. An improvement of the Doolittle LU factorization is the Cholesky factorization. The Cholesky factorization is useful for symmetric coefficient matrices, that is, matrices that are equal to their transpose. So the A12 and A21 elements are equal, the A31 and A13 elements are equal, and the A32 and A23 elements are equal. For the Cholesky factorization method to work, the coefficient matrix must also be positive definite. That is, the determinants of the submatrices formed by each of the square matrices containing elements A11 in the upper right and AII in the lower left must all be greater than 0. That is, A11 must be greater than 0, the determinant of the submatrix containing the first 2 elements in each row and column must be greater than 0, the determinant of the submatrix containing each of the first 3 rows and columns must be greater than 0, and so on. This is called a positive definite matrix. We'll encounter symmetric positive definite matrices when solving boundary value problems that enable us to use Cholesky factorization. One of the things that makes the Cholesky factorization method faster is that the LU factorization requires finding fewer elements than when we use the Doolittle method. Since A is symmetric, we know that some of the elements in U will be equal to some of the elements in L. So instead of finding L and U, we only need to find L and its transpose. In this method, the diagonal elements of L are not necessarily 1. For a 3 by 3 coefficient matrix, we only need to find 6 values as opposed to the 9 values that are required for the Doolittle method. MATLAB has built-in functions that perform both the Doolittle and the Cholesky factorization methods. For any square matrix A, we can find the lower triangular and upper triangular matrices corresponding to the Doolittle factorization using the MATLAB command LU. MATLAB has a built-in function col, which performs the Cholesky factorization of the symmetric positive definite matrix A. When MATLAB performs the Cholesky method, the output is an upper triangular matrix corresponding to L transpose. So A is equal to, instead of L times L transpose, it's equal to U transpose times U. To summarize the direct methods for solving linear systems, we studied Gauss elimination and a modification of Gauss elimination called partial pivoting with row scaling. The partial pivoting with row scaling can enhance the solution method when some elements of the coefficient matrix used for elimination, that is, some of the pivot elements, are very small. We also looked at the Thomas method, which is a modification of the Gauss elimination method for tridiagonal matrices. The LU factorization methods that we introduced include Doolittle's method and Cholesky's method. The LU factorization methods produce a lower triangular and upper triangular matrix L and U from a relatively small number of operations, and then solve for the unknown vector x using a sequence of forward substitution followed by back substitution. In the next video, we'll introduce the indirect methods, which are iterative methods for finding solutions to linear systems of equations.